We show a pipeline for real-time visualization of faces for VR-based telepresence and live broadcasting by utilizing neural rendering. We deal with a problem and propose a solution how VR applications can become more social, vivid, and realistic. The presented work is based on our previous paper, presented at the National Conference of Virtual Reality and Augmented Reality 2020 of the German Informatics Society, and the authors were invited to submit an extended version to the JVRB journal. What is the motivation behind our work? Real face-to-face conversations are not possible in VR yet. The problem is that the face is obscured by an HMD. Classical face tracking methods fail at this point, and also combining several cameras to a complete face is very difficult, since the HMD only provides images from extreme angles. However, it is possible to track individual landmarks such as the iris via eye tracking, or the eyebrows, or even the corners of the mouth and the position of the chin. In a previous work, we developed a working prototype of a face tracking HMD. This system gives us 70 animated facial landmarks shown in the top left corner. Also, HTC released a lip tracking module last year, which can easily be combined with eye tracking. Our goal in the presented work is to reconstruct photorealistic faces in real time from a specific person. We call these black and white images in the top left corner facial landmark maps, and the following abbreviated with FLM. The main question is how can we reconstruct and control a face in a certain facial expression from these FLMs. Especially for virtual environments, we would like to show not only the 2D image to other participants of a virtual meeting or viewers in a broadcasting scenario, but also the entire face in 3D. How can we achieve this? Conceivably, one could, for example, make a single 3D scan of the person and control the 3D scan with the landmarks. However, the avatar would then not be able to control personal expressions because each person moves the face in their own way and, for example, the appearance of wrinkles or dimples is different from person to person. This means you would have to take more scans to interpolate between different expressions, but this has disadvantages. The capture process is time-consuming, requires technical knowledge, and usually needs an experienced 3D artist to create the blend shapes and give the avatar a photorealistic appearance, which is extremely difficult. However, we are pursuing a different path. In the last 5 years, there have been some breakthroughs in the field of neural rendering. We take advantage of a particular technology from this field, which is called Generative Adversarial Networks, according to Goodfellow et al. We present our specialized pipeline and our GAN with a hybrid architecture and loss function from different approaches of the field of neural rendering, which is able to generate images in according 2.5D point clouds of trained faces from our semantic 2D labels, the FLMs. The first step in our pipeline is to generate a training dataset. We built a helmet mount for an RGBD camera. This mount ensures that only data with a limited variety of head distance, tilt and rotation are captured. While we keep the entropy of the dataset low, we ensure to maintain a high reconstruction quality of the trained network, and second, to significantly speed up the training process. After the capture process, an automated step prepares the images for training. First, the images are cropped. Since we are also taking a depth image, we can also crop this accordingly. For the training, it is necessary that we create landmarks to let our GAN learn the image-to-image relation. For landmark detection, we use the facial alignment network by Bullard and Tsimeropoulos. During the recording, the person must show a variety of facial expressions so that these can be included in the dataset for training. On average, about 1,500 to 2,000 RGBD images are taken with the helmet mount to achieve a good reconstruction quality of the person. The acquisition process in the helmet mount takes about 10 minutes. Now we can give the dataset to our networks and they learn within an adversarial training process the relationships between the landmarks and the given RGBD images. After the training, the generator receives FLMs with a size of 512 to 512 pixels as input and generates according RGB and D images with the same number of pixels. This corresponds to a point cloud of about 250,000 points. With clipping and erosion, we end up with about 100,000 points for each face, which can be seen on the right side. The most relevant changes compared to our previous approaches are 3 improvements of the discriminator side of our GAN. First, we added a multi-scale approach, which means the network receives an image with 3 different resolutions, which leads to a better distinction between low, mid and high frequencies in the images as in the Pix-to-Pix HD framework proposed by Wang et al. Second, we changed the sigmoid cross-entropy loss to the LS GAN, the least squares GAN loss, also suggested by Wang et al. And third, we exchanged the perceptual VGG loss from the Pix-to-Pix HD framework with the learned perceptual image patch similarity metric by Zhang et al. The generator keeps mainly the same compared to our basis, the Pix-to-Pix framework by Isola et al. We only added according layers to generate images with higher resolution, and we did not implement a global generator network combined with a local enhancer network as suggested in the Pix-to-Pix HD framework by Wang et al. This way we obtain a hybrid framework between Pix-to-Pix and Pix-to-Pix HD with better image quality by only adding a small amount of time for generation, which makes this hybrid approach suitable for interactive applications with a better image quality compared to our previous systems. Please see the paper and our GitHub site for further details and parameters for a stable training. In direct comparison to our previous works, we increased not only the resolution by 4 times from width and height of 256 to 512 pixels, we also end up with a significant improvement of the reconstruction quality of higher frequency details. Image A, the upper image, is our old pipeline. Image B is our new pipeline. Our improvements also leads to shorter training times because of the combination of more purposeful losses and better hyperparameters for this specific task of generating a face. Our previous system took about 17 to 20 hours for training on a dataset with only 600 RGBD images with according FLMs on an NVIDIA RTX 2080 Ti. The new pipeline needs only 8 hours on this graphics card with a dataset of 1600 images and FLMs. Inference on an RTX 2080 on the previous system took around 1 to 3 milliseconds. The new pipeline takes about 6 to 7 milliseconds with a 4 times higher resolution. Note that the frame rate is usually limited by the tracking systems, which is, in case of the HTC lip tracking modules, 60 frames per second, and for our eyebrow tracking cameras only 30 frames per second. Due to further computation time for tracking, filtering and rendering, we achieve real-time frame rates between 25 and 30 frames per second in a real application scenario. We would like to show some results in motion with a face tracking HMD from our previous work. In the video you see a real-time reconstruction using 5 tracking cameras mounted on and in the face tracking HMD. Basically, we use the HTC Vive Pro Eye with the HTC lip tracking module. In addition, we mounted 2 further cameras in the inside of the HMD to track the eyebrows. The cameras have a refresh rate of only 30 Hz, which limits the tracking rate of the area of the eyebrows. This is a feed from an external webcam. It does not contribute to the tracking and is only shown for demonstration purposes in this video. We concatenate the tracking information of eye tracking, eyebrow tracking and lip tracking into an FLM as visualized here. The FLM is sent to the generator and it creates the RGBD image and the depth image here, and we finally combine color and depth information to a point cloud as shown here on the bottom right. As you can see, our system is able to reconstruct many expressions, though there are some artifacts. Artifacts are caused by tracking errors of the HNB, but also by errors of our generator. Errors around the eyes and the oval cavity can induce the uncanny valley effect and are subject of further research. Another limitation is that lip movements during speech cannot be reconstructed faithfully, as can be seen here.
This is a test.
Please find our code and models on our website. Thank you for watching.